In this new chapter, we will learn about vibrations and waves. I assume you see my screen, right? My PowerPoint?
Yes.
Okay. So we will learn all about periodic motions. A periodic motion is a motion that repeats over and over again with time. This is an important motion in nature that when we study physics, we try to understand all about it. Examples of such motion around us, you have the pendulum. It oscillates back and forth. This is periodic motion. You have a spring attached to a mass. On displacement, it will oscillate back and forth, vibrates. On atomic scale, atoms are in continuous vibrations at all times, and that motion is also periodic motion, repeats over and over. We have waves, sound waves, we have light waves. You see the waves in the ocean, in the open sea. So this is an important motion that we need to understand its physics and the laws that govern the motion. So now we are ready to start learning about periodic motion. And usually the best start, the best example that we are all familiar with is the spring. Consider a spring on a horizontal surface like this, fixed at one end, and consider a mass m at the other end. For the sake of argument, at this point, we assume no friction between the spring and the surface, or between the mass and the surface. So when the spring is unstrained, relaxed, the change here, x is 0, and the applied force is 0. If we compress the spring this way, there will be a force that opposes us, and it tries to restore the spring to its original status. So the displacement is to the left, but the force is to the right. On the other hand, if we stretch the spring, so the displacement will be this way, but the force in the spring will try to restore the spring to its unstrained position, is again acting against the displacement. So whether it is compression or stretching, either way, the spring force will be opposite to the displacement x, and the magnitude of this force is proportional to x. If x is 0, the force is 0. Then the greater the deformation x, the greater would be the force. We change proportionality into equation form by having a proportionality constant. The proportionality constant k here is called the spring constant. And the minus sign is just to tell us that the spring force will always be opposite to the displacement. We call this force the restoring force, because it tries to restore the spring to its unstrained position. This law was discovered in 1678 for the first time by a guy named Hooke. So it was named after him, Hooke's law. It's a fundamental law when we study elasticity, when we study periodic motion. it allows us to understand the full motion as we will see in this lecture. Consider this situation. You have a spring hanging from the ceiling like this. Then we attach a mass at the free end. As a result, the spring will be stretched by a distance d, say, and you have equilibrium situation. We know from our study of physics 1, when you have equilibrium, this means the net force is 0 because there is no motion. Now, the free body diagram here for the system, you have two forces. You have the weight downward, mg, and the restoring force in the spring up, fs. Since we have equilibrium at this point, no motion, so fs minus mg equals 0, or fs equal to mg. Okay? If you increase m, then the stretching of the spring will increase. But for a fixed value of m, there will be a fixed value here for d. Now, if you let the mass to move freely, let go, the spring, because of the restoring force, will try to restore the original status. So the mass will start moving up and down in a periodic motion. And if there's no friction, this motion may continue forever. We define a few quantities here. The maximum displacement, we call it amplitude for the oscillation, for the vibration. So the spring will be oscillating back and forth between x minus a and x plus a. We define another quantity, we call it the period, and by period we mean the elapsed time for one complete cycle. By a complete cycle we mean the motion from x equals a to x equals minus a, and then back to x equals a. This is a complete cycle. The time needed to finish such a cycle is called the period of oscillation, and usually we use uppercase T to represent this period in equations. The third quantity that we need to describe the periodic motion is the frequency. We use the symbol F to represent this quantity, and we define it as the number of cycles per second. The number of cycles per second. The number of complete cycles from A to minus A, then back to A. This is a complete cycle. The number of such complete cycles per second is called the frequency. We can get that number simply by dividing 1 second to the period t. So 1 divided by the period will give us the frequency. Now, for the acceleration, as we learned in mechanics in physics 1, from Newton's second law, the net force is equal to mass by acceleration. And in this case, the net force is the restoring force, which is from Hooke's law, minus kx. So now we can calculate the acceleration for this motion easily. ma equals minus kx, therefore a, the acceleration, is minus k over mx. Again, I'd like to stop a little bit here on this equation to understand what's going on. First, the minus sign. The minus sign just to tell us that the acceleration will always be opposite to the displacement. The acceleration of the oscillating mass attached to the spring, the acceleration will always have a direction opposite to the displacement x. If x to the right, acceleration will be to the left. If x to the left, acceleration will be to the right. The second thing is the mass. As we can, the greater the mass, the smaller would be the acceleration. The bigger the mass, the smaller would be the acceleration. The third observation is the dependence on x. The greater the deformation, the greater the stretching or compression distance, the greater would be the acceleration. If x is 0, no stretching, no compression, then acceleration is 0. Acceleration is 0. So if you go back here, when x is 0, there is no acceleration. The greater is x, whether it is compression or stretching, the greater would be the acceleration. Now, the greater value for x is the amplitude. The greater value for x is the amplitude. This is how we define the amplitude, the greatest displacement from the unstrained position. Because of the proportionality between the acceleration and x, so when x is maximum, when x equals a, then the acceleration will be maximum. So a max, now we understand how it will change from minus ka over m to plus ka over m. And we understand this business of sign. The acceleration direction will always be opposite to the displacement. Check your understanding. A hook on the end of a horizontal spring is pulled from equilibrium at x equals 0 to x equals a and released. Through what total distance does it travel in one full cycle of its motion? We have these suggestions. Any suggestion? So it is 2a in this case. Okay, this will be the total distance in one full cycle. In one full cycle, you have 2a. Okay, to minus a, then to plus a together, it is 2a. Another question. For a simple harmonic oscillator, which of the following pairs of vector quantities cannot both point in the same direction? Cannot point in the same direction. The position vector is the displacement vector from equilibrium. You have these three suggestions: position and velocity, velocity and acceleration, position and acceleration.
I think it would be number 1.
Number 1, position and velocity. Thank you, Victor. Lindsay, what would you say? Any suggestion? In fact, it's not number 1, because position and velocity, most of the time, it's the same direction. But position and acceleration, as I explained earlier, position, that is x and a will always be opposite to each other. Okay? The force and the displacement will always be opposite to each other.
Okay.
Yeah, thank you.